Okay friends, we will try to solve another problem on singly reinforced beams, that is 3.6.2. Again, I did forget to mention about the textbook while solving the first problem. So it is our regular textbook. The title of the textbook is Illustrated Reinforced Concrete Design, 3rd edition by Shah and Curve. So we are solving the problems on singly reinforced beam. So let's start with again the second problem, 3.6.2. I will read out the problem for you guys. A simply supported beam of 4.5 meter span carries a uniformly distributed load of 30 kilonewton per meter inclusive of self weight period. The width of the beam is 230 millimeter and is reinforced on tension side only period. Design the smallest concrete section period. The material used are M20 grade of concrete and mild steel reinforcement period. Assume load factor equal to 1.5. So this is the problem. So we have to find out the smallest concrete section. So if you notice, already B is given, right? So our job is to find out uh, this small d, right? Our job is to find this small d, and we have to find out this capital D, and also we need the area of the steel also, or what is the AST, right? So these are the things we have to determine to design the smallest concrete section. So let's start with this problem. Uh, so already materials are given, so we know that FCK is 20 Newton per millimeter square. F is given in mild steel, so Fy for the mild steel is, that is 250 Newton per millimeter square, and B is given, that is 230 mm. L, span of the beam, is given 4.5 meter, and one more thing is given, that is small w, or W total, we can see 30 kilonewton per meter, and this is inclusive of the self weight, so we don't need to add the self weight again in this quantity. And the LF, load factor, is given as 1.5. So let's start with the uh, uh, let's start to find the smallest section. So we don't know the D, right? So ultimate aim is to find out the D. If you know the D, we can find out the D. So D, capital D, will be D plus D dash cover. And another thing we have to find out here is AST, right? Let's start with the D first. So how to find out the D? To find out the D, uh, we need to use this formula, if you remember. So D will be equal to square root M EU into RU max into B. So this total quantity is under square root. So if you remember the formula for this quantity, right? RU max. If you know the formula, then you can find out the so RU max, if you remember, or if you remember the formula for this MU, anybody, doesn't matter, right? MU will be equal to RU. MU is equal to, or I will write down the formula here. MU equal to RU into BD square. So if we re-engineer that formula, then we will get this formula. So now to find out this D, we need to find out the quantities in the um, uh, in this formula. That is, I will write it one more time here. Mu divided by Ru into B. So B is known, we have to find out the Mu. So Mu we is equal to 1.5 W L square by 8. So this is load factor, this is total load, total uniform load, or the weight. L is the span, and this is divided by 8. This is for simply supported, right? Simply supported beam. This formula works well. So plug in the values. 1.5, W is given as 30 kilonewton per meter. L is given as 4.5, square of that divided by, so Mu quantity will come to 11 113.91 kilonewton dash meter. So once you know that, now the second quantity from the formula is Ru or Ru max. So formula for this is 0.36 FCK into Ku max, right? If you remember the formula, Ku max into 1 minus into bracket 1 minus 0.42 Ku max. Ku max. So we don't know this Ku max, so we need to find out the Ku max. So Ku max is called neutral axis factor, right? So formula for this is max, that is for balanced design. So it is 700 divided by 1100 plus 0.87 Fy, right? This is the Ku max formula. So plug in the values. 700 divided by 1100 plus 0.87 Fy is 250 milestone, right? So Ku max is equal to 0.53. So now this Ku max will go here, right? Here and here to find out the Ru max. So Ru max, I will write the formula one more time. Ru max equal to 0.36 FCK, 0.36 FCK Ku max into 1 minus 0.42 Ku max, right? So now plug in the values. We have almost all the values. 0.36 FCK is 20, Ku max we already calculated, 0.53 into 1 minus 0.42 into 0.53. So Ru max will come to 2.97 Newton per millimeter square. So once we have these values now, so we have the Ru max and the Mu, and we of course know the B, so we can find out now D. So D, that is the depth until the center of the rods or the steel rods, is equal to this formula. Again I will write it here. Mu max, Ru max into B. So plug in the values. So square root or under root, Mu is equal to 113.91, but this is kilonewton meter, so convert into Newton millimeter, right? So that's why we need to multiply that quantity by 10 raised to 6, because our Ru max is in Newton per millimeter square. So Ru max is 2.97 and B is again in millimeter, that is 230 millimeters. So that's why this quantity we have converted into from kilonewton meter to Newton millimeter by multiplying this by 10 to power 6, right? So from this we can get now D. So D will be equal to 408 millimeter. So you can see that we have designed this section or find out the this quantity for the balance or the maximum D, right? So this will be the D for our uh, for concrete section. Then if we know the D, we can find out XU max. Actually it is not required, but just find it out. So I will just explain what is XU max. XU max will be the Ku max into D. In case you want the depth of the neutral axis, you can find out the depth of the neutral axis for balance section, that is XU max. So now we have the D now. We don't know the we don't know D dash, right? So because capital D is equal to D plus D dash, so it will definitely goes with the of size of steel bars or the size of the bars. but we are not going into details of that. Definitely this d dash or the cover uh, should be more than the size of the bars, so we are not going into details, but right now we are assuming this d dash equal to 50, or you can assume 55 also. uh, Generally there are recommendations for assuming d dash. Different recommendations are there, different recommendations I will write here only, or different considerations are required. So right now we, for this formula, we are assuming d dash as 55 millimeter, that is cover. So generally this d dash should be more than the dia of bar. So this is general criteria: dia bar or steel bars or the steel rods. So our capital D will come to d plus d dash. So already d we found out, that is d is 408, plus we have assumed this d dash as 55, so this will come 463 mm. You can keep this or uh, round it to the uh, next value, multiple of 10. So this will come to a d equal to the 470 millimeter. So once we have that, so we can have the size, right, size of the bar. So this is b, this is b, and this total is d, but still we are missing the size area of these steel rods, or AST. So we have to find out the area of the steel rods. So formula for this AST will be equal to, so 0.36 FCK into B into XU max. Here we require the XU max, so we need to find out that. Then 0.87 FY. So find out the XU max. Already we have given the formula, right? XU max will be equal to KU max into D. KU max already we have found out, that 0.53 into D is 408. So XU max will come to 216.2 millimeter. So now use this value for getting this AST, or put in the AST formula. So again I will write AST formula will be equal to 0.36 FCK into B into XU max divided by 0.87 FY. So now we have all the values, just plug in 0.36, FCK is 20, M20 grade concrete, then B is 230, right, into XU max is 216, just we have calculated 216.2, right, and then divided by 0.87 FY. So this AST will come to, if you do the all this this FY, I will enter the actual value. This is 250, right? So this is 250. So AST max, or AST for the balance section, will come to 1646.1 millimeter square. So now we have all the quantities, the parameters to define the smallest concrete section. This B is 230, this capital D is after rounding 470, and the small d is we have already calculated small d, that is 408, and these are the steel rods. They have the area of 1646.1 millimeter square. So now we have all the quantities, and this is the final answer. Thank you.